Random forests are by far my favorite machine learning algorithm. So what's the basis of a random forest? It's a decision tree. So imagine we were trying to classify an animal. We have three animals. We have a giraffe, we have a dog, and we have a horse. Giraffe one kind of sticks out there. Now, let's say that these are the only three possible animals that we're trying to classify. Now we can start off basically with a decision tree by asking a list of questions. So we know things about these potential animals that are out there. We have a new animal, we're trying to decide, is it a giraffe, is it a dog, or is it a horse? So we could ask a question like, does it live on a farm? And in this case, if you're, someone who's been on a farm, you realize that horses and dogs have both been on there. Could both be on there. You might be a bit more critical, you might say not, but let's say that if they are on a farm, then if they're not on a farm, it's probably a giraffe in this case. And now we're left with a dog and a horse. How do we decide whether or not it's a dog or a horse? We can say, can you ride it? And for most dogs, it's probably going to be a no. So that's a dog, and then we have a horse. So we've effectively found two variables, whether or not it lives on a farm, whether or not you can ride it, which can classify any new incoming information into the picture. So we can say as long as we know these two things and we know that there's only three possible animals, we can pretty effectively separate out which animal it is. What if it gets a little bit more complicated? What if instead there's numbers? So let's say rather than knowing whether or not it lives on a farm, we know how much time it spends on a farm. So that first variable, or x1, is the variable of percentage on a time on a farm. And our x2 is how much percentage of people who can ride the animal. So, you can imagine something like a dog, if it's a big dog, and, maybe there's a child, maybe the child can ride the dog. It's all for the sake of just a demonstration. Percentage rideable. And let's say, for example, we had another variable. Let's say we actually have a lot of information on these animals. We might have, what happens with big data, with large data sets, with all kinds of information coming in. We have another variable that might be, on the surface, pretty useless. So let's say it is, for example, whether or not it swims. So this is one variable. So let's say maybe not swim, whether or not it can breathe underwater. So percentage breathing underwater. Now, that might be useful for some animals. That might be useful for classifying if we had a dolphin versus a whale. But realistically, with our data, breathing underwater is pretty useless in determining which animal it is. So this is actually quite important, and this is actually the strength of a decision tree and a random forest. We have information that is kind of useless, and what we're doing is we're saying that we're gonna have a rule that says we're not going to use that information. We're not going to make a decision on it. So when you're constructing a random forest, and let's say you don't know much about animals, but you know how giraffes and you might have some information on giraffes and dogs. You might have this is your y variable realistically, and then percentage on a farm, percentage rideable, breathing underwater, and just like in other cases, for some of them what giraffes and dogs and horses are, and some of them you don't, and you want to figure out which ones. For the ones that you don't, which animal are they? So that's the whole training and test data. So the rule is for a random forest is called impurity. Now, the way impurity works is you want to split at a node, which is where you make the decision. That's called a node. And you want to be able to split it into the most distinct groups. So how a decision tree is formed is through an algorithm. Is you looking through these variables and you're trying to see which ones split the data the most. So we're going to start with a random variable and we're going to say, does this split the data in a meaningful way, in a particularly useful way? So if we start off with breathing underwater, if we go all the way to here, we can assume that given that all the data that we have is either giraffe, dog, or horse, that none of them, not a single one, draw the empty set, not a single one is going to be breathing underwater. Now all of them are going to fall in here. That's actually a bad rule. Now the cool thing is, because we're using a random forest, because, well, just a tree in this case, we're going to eliminate that. We're not going to use x3 because it doesn't do that much. We're going to check all these other x's and see if they perform any better. So like we already did, percentage rideable, percentage on a farm. So if we select whether or not it's rideable, then giraffe, horse, dog, yeah, it turns out that we can actually split pretty well. Maybe you can ride a giraffe. I don't actually know if you can ride a giraffe. I'm uncertain about that. But let's say you can. Let's say you can for the sake of argument. They're pretty rideable. And then so we have rideable. And we have, we'll say no's to the, so this would be like a no, and that's like a yes. So no would be a dog, and then a horse and giraffe. So we check that and we see we actually split it pretty well. There's ways of determining this mathematically based on like the data that you have, what is like good split into how sensitive that is. But in this case, it split it better than than x3 over here, which is percentage breathing under the water, which didn't split the data at all. It was pure. It was a pure characteristic. And this one's relatively impure. And if we were to do the same percentage living on a farm, we'd probably find something similar. We'd find these two would be looped together and that one would be separate. So this is how decision trees are really made. Now, rather than getting into the math of it all, because that's something you can look up easily and get more into, the logic of a random forest is very similar. It's an ensemble. It's an ensemble of these decision trees, which are formed by maximizing the impurity in each of them. So let's say you have a given set of data. Now, what you want to do, let's say you have a pretty good decent amount of data. So you have you have observation 1, observation 2, 3, 4, 5, 6, 7, 8. And the last example, these would all be animals. And what we're going to do is we're going to pick out, oftentimes with replacement. So this could be, we could pick out a group that's the exact same size of the entire group. So this would be 1, 2, 3. We're going to do this randomly. So then there might be 2, 1, 2, 3. We're going to do that a bunch of times, and we're going to create separate decision trees for each one of these samples. Now, on a high level, what that does is it stops us from perfectly fitting the data. Because when we have incoming data we want to be able to make good decisions based on the new data, not to perfectly fit the old data. So we have our what's called bootstrap samples, and we're going to create 3 different decision trees based on it. 3 different decision trees. And in a lot of cases, they're going to look quite different. They're going to split on different variables. You're going to split on different x's. You're going to have different split off points. You're going to have a variety of different, you may have a variety of different features. And what's going to happen is that you're going to give all of these equal weight. So we have bootstrap 1. I'm going to call that B1. I don't know if that's actually how they represent it. They're going to have B2 and they're going to have B3. And you're just going to take, when you're making a new prediction about a new point, so let's say we have our x1, x2, x1, x2, x1. This is just all as if this is what they came up with. You're going to run it down the trees. You're going to figure out what it's classified as, and you're going to take the average. Or in this case, probably the mode, because animals don't exist on an average. If it was a number, you take the average. And let's say this one, we ran a new point through. We'll call this x question mark. And we got a giraffe here, we got a dog here, and then we got a giraffe here. So within the random forest, we ran our data through, and we got giraffe, giraffe, dog. Well, we're probably going to classify it as giraffe. And what the cool thing about this is, when you work with large data sets, when you work with large features, and you're trying to classify new points, this ends up being a really effective way to make new predictions without fitting things too close to the data. If you know what overfitting is, then you want to avoid that as much as possible. And random forests are actually a really good way of avoiding that overfitting problem. And you also get some interpretable results by the end of it. So when you're running new points through, for example, when you are running new data through your test set, you're going to get a test error by the end of it. So it's going to be there's going to be an error value. Now the thing is, what you get that's interpretable from this is you get errors for each of the trees. You can get errors for each of the trees. You can get errors for the entire forest, error values, whether or not classified it properly. So in this case, this one had an error. This one classified that point improperly. This one classified it properly. This one classified it improperly. The output that you get from a random forest, other than predicted values, is variable importance. So when you add that variable to the table, so let's say this was x3 and this was percentage breathing underwater, if you remember, we'll see that adding it didn't add anything to the prediction value in this case. And so what you're going to get as a result, including your predictions, is a variable importance table. I'll just put VIM or VIMP. And it's going to list all the characteristics that were found to be useful in the model. I'll explain how to do that another time and how to interpret that. And additionally, there's another extension of random forest as well, rather than just the output, which is where you can run a gradient. You can do gradient tuning, and you can decide, rather than taking the mean of all these trees, you might try and add a coefficient to it. So maybe this will be C2, C1, C3. And just like in k-nearest neighbors, and just like in many machine learning algorithms, we can run the data through to select optimal values for these, for example. So random forest is interpretable, it's generalizable, and it's also customizable. And that's why it's a really good machine learning algorithm.